This is a presentation I usually do with Helmut Nagy out of GraphWise. We teamed up with GraphWise to build this model and published a full, large paper explaining every detail of it and how you can implement it yourself. We say it's powered by DITA, and I don't want anyone to misunderstand that. On this call, we have people who have audacious code. They use Markdown, they use Git, they use ASCII doc. This model supports all of those content types in a knowledge graph to go far beyond where 95% of development organizations are today with RAG, with retrieval-augmented generation, leading to far greater and more powerful applications. I did ask this question of OpenAI, of ChatGPT, is AI smarter than a fifth grader? And I got a bunch of answers, but then I threw a basic question at it, and I said a dead cat is placed into a box along with a nuclear isotope. The box is opened one day later, and what is the probability that that cat is still alive? And I wasn't surprised with the answer, and that's because ChatGPT doesn't really reason. They use the term reasoning as a recursive pattern matching capability, but it's not deductive reasoning or deterministic reasoning like we would typically define reasoning. But yeah, it comes back in most cases. It will tell you that thinks the cat still has a 50% chance of being alive, the dead cat. And I kid you not. This is a good example of how large language models really don't have the reasoning capabilities they purport it to be with large context models and other techniques. They improve the large language models a little bit, but until you introduce deterministic external sources of facts like a knowledge graph, you really don't have reasoning in the classical sense that's reliable 100% of the time. Helmut Nagy has a great quote here: knowledge graphs give the content context and structure, making it intelligent content. And intelligent content combined with AI will be the driving force behind truly trustworthy AI solutions. We're going to show you why. And my quote, I've managed content teams. I built technology and strategy for IBM. We had upwards of 1,500 technical writers at one point. We had 60 million pages of content on our portal for 3,500 products in 50 languages. So, I know pretty much what true content management and operations really are, but the way these current models are actually architected are not taking into account true end-to-end lifecycle and content management. And I think that's tantamount to professional content management malpractice, and I'll show you why and how you can get around that and solve that problem. So the motivation for this project were all the things that you typically have motivation for to use AI, right? We want greater accuracy, we want higher relevancy, reliability, explainability, and trustworthiness that the AI-based models don't give us out of the box. We want our customer sat. We want our customers to be happy and use our products. We want them to do their own self-service much faster than they can by opening a support ticket and give them the information through a chatbot and other mechanisms to get them to get onboard them faster. I mean, it's no good if a customer signs up for your product and doesn't use it at that point because the onboarding takes too much. We want to guide them through that onboarding. Most importantly, we want our customers to achieve time to value, right? The sooner they get the value out of the products that we offer, the sooner they're going to come back as happy customers and buy more, upsell and cross-sell, and make more profit. So they win, we win. Of course, keeping your customers once you've got them is your bread and butter of your business. And personalization. So this phrase down here originated at IBM in the early 2000s. It's become very common in the industry. Is we still want to provide the right content to the right person at the right time and in the right experience. And that's what drives the motivation that we have. When I started this, I started with AI back in 1990 when it was called Expert Systems. I was developing AI in the era of Watson in the mid-teens of the 2000s. And then I started with knowledge graphs in the late teens of the 2000s and started with ontologies and taxonomies. And as I would present this at conferences, the people's eyes would glaze over and start tearing as I started using terms like SCOS and OWL and other technologies. It just wasn't normal for typical content developers to play in the knowledge management world. And I knew I wanted to have a graph, but I didn't have one. I was working with some really smart people, colleagues at Microsoft and a few other places that were manually building knowledge graphs at the time. And I said, this is crazy. It's not sustainable. We have to have a way to automatically create knowledge graphs from our smart content. There's got to be a way to do that. So what are our AI teams? We have a big AI ML team here at Avalara. We're extraordinarily invested in AI for years. With traditional AI for many years that drive Avalara's sales tax automation that backs sites like eBay and many other sites. We do all the automatic tax calculation for thousands of jurisdictions. Calculate tax calculation, returns, filing, licenses, you name it. So we've been using AI for a long time, and now for the last 3 years, we've been really diving deep into the generative AI space. But the vector-based models that we built starting 3 years ago, they work. But the problem is they fail to meet expectations when you get into more critical apps. Perfection is not required to create a support chatbot, in fact, right? You can deflect 20, 30, 40, more 50% of customer support tickets very easily with a faulty chatbot that doesn't return an answer all the time or actually hallucinates some of the time. And many companies have deployed chatbots that do this. The value is high. It's not perfect, but there's so much value that it doesn't make sense to not deploy something that may not be perfect. In-app chatbots sometimes do a little better because we know exactly the product that we're in, so we can narrow the corpus in our RAG environments to just that content. So they tend to have a higher degree of precision, but not significantly higher. But they eventually hit a ceiling. And I have not seen a single vector-based RAG model that really can do, consistently better than, say, 60, 70, 80% max. And that's not good enough for the critical applications like agents that have to be decision makers that are coming. So there's this notion called the precision paradox. And here's how it goes. As your system gets better and better, and it does, you hit those those medium percentage points, everybody's celebrating. They're popping the champagne corks because guess what? We're, deflecting 30, 40, 50% of our support tickets now. It's wonderful. And then the party starts to die down because the better that it gets, the more dissatisfied users get with the degree of inaccuracy that exists. And that's called the precision paradox. That's why we need to move from these current predictive systems, which is what almost every implementation is these days, because we've got a predictive large language model, and we're building RAG models based on predictive vector databases, surfing two predictive models on top of one another, and you wonder why it hallucinates, and you wonder why it doesn't always return, high degree of reliability, because they're not truly deterministic models. So the companies are finally realizing, and you've probably heard this a lot today, right? The need for more and better context to feed these large language models. What's missing are fact-based, what we call deterministic reasoning and inferencing based on, that's really based on something solid, like a defined and curated knowledge graph. These notions of reasoning that the large language models are putting out, like chain of thought or vector math, really are not reasoning. I published a paper on my website. It's a sizable paper. It describes all the different kinds of reasoning and inference. There's actually several dozen different flavors of reasoning. And if you ask somebody that claims that large language models reason, you can ask them, well, what kind of reasoning? It is predictive reasoning. It'll hallucinate, And if you have a chain of thought where a prediction is wrong early in the chain, it actually can corrupt the entire chain, which nobody really talks about. So we really need to move to fact-based reasoning. And so, well, let's get to the point. So AI engineering teams, they're typically under pressure from senior management. This is not unusual. This was true here at Avalara. They quickly, it takes a week roughly for a basic Python programmer to write a little bit of Python code, take your content, ingest it into like a Pinecone free open source database, and start producing a RAG chatbot. There's probably more work in just producing the UI than even building the RAG model. We did that 3.5 years ago and realized immediately it wasn't going to be enough because the predictive Achilles heel of that model. And they keep trying to find workarounds. They try to tune the large language models, try to tune the model, and something happens called over tuning. And the problem is that, okay, if that doesn't work, well, maybe we should move to something more deterministic based, like knowledge graphs. And they face the same problem that I faced early on, which was, well, how do you build these large graphs of all this massive amount of content? You can't really sit there and construct these nodes in a graph manually. There's tens of thousands or hundreds of thousands, even millions of nodes in a knowledge graph. So what they do is they turn to the large language model, which is a predictive engine. So yeah, it can be done with a large language model, but the human has to do an immense amount of human in the loop correction and additions to it. It's the slow way and the dangerous way to try to generate a knowledge graph because of that highly predictive and hallucinating model. It can be used when you have a knowledge graph, and it is a curated knowledge graph. It could be used to add to the knowledge graph as long as you're curating the results from the large language model, because you don't want approximation. The whole point of having a knowledge graph is to have an absolute fact-based corpus to validate the answers that you're getting from the retrieval to feed to the large language model. So I built this maturity model a couple of years ago, and it sort of works like this. At the very base, what we want is intelligent content containers. What do I mean by that? Well, if you've got Markdown and you've broken, or you have ASCII doc, you've broken down your content into topical-based models, and you've added some metadata, you've added some taxonomy. Those are containers, right? If you've got XML or DITA, for example, you have even more highly containerized things. Not only is the document containerized at the file level, it's containerized all the way down to individual elements like dangers, cautions, tasks, steps, procedures, and all kinds of things. So it doesn't matter. I don't care, what you're using. If you're using Markdown or you're using RST, I consider those to be containers. And the more that you add intelligence to those containers in the form of metadata or taxonomy, the more intelligent they become. But you also have to have a solid base of terminology. If you try to build taxonomies and ontologies and knowledge graphs without a solid terminology base, you're building a house of cards that's going to collapse because your terminology has to be consistent through all of these structures. Your next step is to build a taxonomy, which you're going to use for classification to actually label your topics as to what's the subject, what's the product, what's the purpose, who's the audience, and you're enriching your containerized content so that we can do things like named entity recognition when we retrieve content through knowledge graphs. The ontology is sort of under the covers. Those are the relationships between objects that you have. So if you have a bunch of content objects, they're related. Sometimes you put them in a hierarchical order. Sometimes you put links between them. And the ontology is sort of like the blueprint that gets loaded into a graph database. And when you load your content into the graph database, magically it can create the entire knowledge graph. And then you can do your AI tools and applications on top of that. And I'll explain that a little bit more. So I use DITA, a document object model graph. Like I said, this does not just apply to DITA. Okay, we're using the DITA map schema to automatically build a knowledge graph that can consist of Markdown topics, ASCII doc, like I said, RST. Pretty much, we prefer text-oriented, topic-oriented components. If you've got DITA, it'll be more powerful, but it doesn't have to be that way because we're not requiring that the topics themselves be in DITA. We can map those into the same graph to do that. So what we did was we wanted to preserve the original context of our content. When you bring content into a vector database, what it does is it rips it up into small chunks and it throws away the metadata, much to people's surprise. They think the metadata is preserved and it really isn't. You have to go through huge hoops to try to create embeddings to keep your metadata and associate it with all of those random 4K chunks that are created. So the fallacy is people think if you put your metadata in your doc file, it's going to be used by either the vector database of the RAG model or the AI itself. And the answer is it really isn't, and it's not really used in any intelligent way. And I'm sorry to burst the bubble of people that think that, but that's a fallacy. What we realized was that we had a schema, and the schema we used was the DITA map schema. That's a collector document to actually reference one or multiple topic files. And again, the topic files that are referenced can be of any content type. We knew that we had already chunked our content into DITA or Markdown or whatever we had, and we can enrich those content containers. Like I said, if you've got a Markdown file, you can add metadata, you can add taxonomy. If you've got DITA, you can do the same thing with those topics. You can even put taxonomy on individual elements in the XML, which makes it even more granular in terms of specific retrieval. If I just want to pull a small chunk of content out of the middle of a topic, I can do that with DITA, where I can't do that with, say, Markdown or ASCII doc. But that's okay. Most of the time, the content that you want to pull are typically the topics themselves, whole topics. And that helps with that named entity recognition. So like I said, it supports all of these models, all of these content types. Here's the problem though. When your metadata is thrown away, when the vector data, when your content's ingested into the vector RAG databases, your metadata is gone. Okay. If somebody wants to show me a model where they've retained their metadata and associated it with all those random chunks, I'd love to look at your model because it not only is that extraordinarily complex to do, it's possible, but it's super complex. It's also not manageable, not permanently manageable. What you want is you want to keep all of your metadata, all of your taxonomy, all of your attributes, all of your links intact with your topics, and you want to retrieve the topics themselves in the whole, not have them shredded into a vector database. And we do that using a graph database, not a vector database. And I'll explain how we built it and how you could build it very, very directly. The problem is that when you throw away all that metadata, you've thrown away all the context. You've thrown away your links. You've thrown away your taxonomy. You've thrown away so much. You've lost the context because you don't have a whole topic anymore. You've got chunks of topics. You've lost your relationships, either the hierarchies that you architected or the linkages. You have entitled content that's labeled for only certain customers that are only allowed to see certain content or licensed for it. Document version control. If you've got multiple versions of your content, if you use conditional inclusion and exclusion, that's all thrown away. Go try to selectively unpublish and retire content from a vector RAG model. Go ahead. You can't do it. You got to rebuild the entire vector database to get rid of it. Multilingual support. How do you pull the right language of the right topic? There's ways to do that with vector databases. You have to create separate vector databases for every individual language that you have to do this, rather than a graph retrieval, which allows you to pick the right, to query and grab the right language document or topic on the fly from a single graph database. Revision management, ability to personalize, change management for taxonomy. Once you classify your content, how do you update your RAG model so that your taxonomy changes all the time and the classifications on your topics change all of the time? Once you've ingested content into a vector RAG model, it's almost enshrined permanently. Okay, and unless you rebuild that vector model again, your taxonomy changes in your source, and now your vector rag model is out of date almost overnight. It's rather crazy. It goes on and on, right? The problems here is that, with a graph, you can update your content overnight, every night, right? You can re-import your content into a graph database, and you're not breaking it up into vectors, and you're not. And the biggest issue is you're no longer dependent on a predictive retrieval model. You're now using a truly deterministic model, and every content, every topic that's represented as a node in that graph carries with it its metadata needed to manage it. And you can use this to augment those existing vector RAG models, which are good for unstructured content. They're very good for unstructured content. But if you've structured your content into topical models, or even higher structured models, then why lose all of that context, all of that capability? So, the other thing is that traditional RAG and vector and large language models don't really do true inferencing. Okay, this is the more deterministic inferencing. And the beauty with inferencing is it really requires to have an inferencing engine, a dedicated inferencing engine, which is not what a large language model is. Graph databases actually have dedicated, integrated inferencing engines that can do this sort of deductive inference relationships. And what it can do is, once you build a graph, the inferencing engine can extend your graph. You've defined explicit relationships between topics, right? You've either done a hierarchy or you've done links. Guess what? Those are your declared relationships. With inferencing, your graph can automatically find new connections between topics that are related that you didn't even explicitly define. And so your graph can actually grow itself with an inferencing engine. The beauty of a graph is it differs from a vector RAG model, because in a vector RAG model, it's going to go get the most likely chunk, right? But what if you need 3 topics that you've written and they're not adjacent to each other? Maybe they're 10, 20, 30, 40 hops away from each other. With a graph, you can retrieve the 3 related topics and bring them together to feed to the large language model. Now you've eliminated the predictive retrieval of a vector RAG model, and you're only asking a large language model to summarize at that point. So you've massively reduced your hallucination risk and inaccuracy risk by removing this stacked predictive architecture that exists in most models. And reasoning, right? This is what we call, you got 2 kinds of reasoning. You've got pattern matching, which is what the large language models purport as reasoning today, which is not very good. And then you've got true deterministic reasoning. And that's what these models do. I wrote this paper called Within Reason, a survey of reasoning and inference models. You can get to it on my website. It's called thinkingdocumentation.com. I encourage you to go there. My papers are there and that describe all of these things, including this entire DOM graph RAG model. So the result was let's put this to the test. Let's really build it, right? Let's not do theory. Everybody's doing theory these days. I want to see real implementation. I'm an engineer. I like to see working models. We were actually able to take the graph, to build the graph, and then use the graph database instead of a vector RAG database to do the retrieval accurately. And we tested it against awful number of QA pairs to validate it. But you can see in this model also that those highlighted fields, those are related concepts that if you click on them, if I were showing you a live version of this, would take you to those documents, would actually retrieve and bring back those related documents that are identified. So we have a recommender system built into this chatbot, not just an interactive chatbot that you would typically see. Like I said, we tested a boatload of questions. So how do you create one of these? And usually when you go to conferences or you have webinars, everybody's always talking about, the next great, hype thing is whatever. And they don't tell you how they built it or how you could build it. Well, I have nothing to sell you. Like I said, this is an open model. It's fully documented in detail on my website, thinkingdocumentation.com. And it really requires 5 simple steps. It's incredibly straightforward. You already have, most of you, your content in componentized form, right? You've broken down your content, hopefully, into topic-based model. Some of you have gone further. You've actually created different types of topics. You know, the basic model of, we like to separate task topics, concept topics, from reference topics, from API topics, and from Q&A topics, right? Many of you have done that. So you've done the hard work already, and the goal now is to preserve all of that hard work that you've done. So we can create a graph, and a graph is made up of triples. Basically, you've got each object has a relationship to another object. Could be topic A is linked to topic B. One is a child of, or is a parent of that. And so our graph that we're going to construct here automatically can use the relationships and that DOM graph model to automatically build these graphs with all of these relationships intact. So the first step is we take the DITA map schema, not the DITA topics, right? Just the mapping schema, and we converted that to an ontology. As I said, an ontology is we load that into the graph, into a dedicated graph database, a true graph database, not a vector database. And we can do that automatically. Basically, the DITA schema, the map schema, the collector schema maps one-to-one almost to an ontology. The ontology is in a form called OWL. And guess what? Somebody did this in 2013, we discovered, Colin Maudry, and he put it on GitHub as open source, as free to use. So we actually started with that, and we took Colin's ontology that was based on the DITA map schema, and we updated it a little bit because the latest DITA map schema has a few additions to it, but you can start there and jumpstart. And what you do is you convert that schema into an OWL ontology, pretty straightforward. And what you do is you then convert your content, whether it's DITA or Markdown or whatever, into a format called RDF, Resource Description Language format. That is a form that is loadable into a graph database. So the way you do it is on a DITA map, inside of a DITA map is something called a topic ref. So on a topic ref, you can point to a DITA topic, you can point to a Markdown topic, you can intermix them together, actually, RST topics. And you now have a hierarchical tree based on a schema of the relationship of all of your topics to one another that you can now build this graph from. So it does require that you create a transform from, let's say, Markdown to RDF, or ASCII doc to RDF. There's an out-of-the-box one for DITA today in the DITA Open Toolkit, but it exists. The next thing you do is you want to make sure that you enrich your topics with taxonomy. So you need to define a good taxonomy, ideally based on your domain, right? Whether it's the medical domain, the legal domain, the software domain. For me, it's the sales tax domain. And so what you want to do is we want to be able to have a consistent list of product taxonomy labels, a consistent list of purpose labels, a consistent list of different audience labels, and we assign those as metadata inside of our topics. There are auto classifiers that do a pretty good job of extracting those and putting them in your topics for you. You have to do some configuration work and testing to get it right, but you can do this at scale automatically pretty well. So that helps with named entity recognition when you query the graph to retrieve or interrogate your content. The other thing you can do is you can, you can start adding concepts about, about your domain space. Right? I'll talk about that in a second. The next thing that you can do is you now have an ontology, right? You've taken the DITA map schema, you've created an OWL ontology. We load that into the graph database, very simple. It's a single click import, right? We then take the RDF stream. We just processed it like another output, just like you create HTML output from your Markdown or from your DITA, whatever. We just take the RDF as another output, and we load that into the graph database. And the process of loading the RDF stream into a knowledge graph database that has an OWL ontology is it automatically builds the graph that is then queryable and maintainable. The beauty of this is you can keep re-importing your RDF stream. You can do it every night if you want to do it. I think our average guide was a couple of 100 pages. We imported the RDF stream into the graph in a couple of a minute, maybe half a minute to a minute and a half, sometimes even less for not as large docs. And you can do that overnight because you've been updating your source content, right? Your product's been changing and you've been updating your documentation. So you can refresh your graph on a daily, nightly, weekly, whatever basis you want to. The beauty is that not only does it bring your topic, these nodes represent your topics, the nodes actually contain all the metadata that you put into your topics. So all of that is preserved and updated every time that you re-import your content into the graph. You can make it a super graph beyond that, right? This now creates an automated graph for us that we can maintain automatically and can query. But if you take your domain specialty, maybe, like I said, I'm sales tax. So I start making, adding additional nodes to the graph. That something like that is a tax system that applies in Europe. That is an additional relationship that I can add to the graph. Now our graph becomes a super graph because it understands the concepts of my particular domain, and that gets mixed in with the structural graph that we automatically generated. And this can be done over time. It doesn't need to be done day one. You could just use the structural graph and you're automatically going to be better than a vector rag model overnight. Adding those conceptual ontology triples, as we say, will make it on steroids, where it really can do reasoning and logic simply using queries to do the retrieval and interrogation. So now we have our knowledge graph, and we have it on a factual basis, not on a predictive basis. And you can see all of the relationships that are automatically created for us as part of using this mapping model. By the way, this mapping model is not new. This is how AI has been done with relational databases for years. Relational databases have schemas. And they figured out a long time ago that if you take a schema and turn it into an OWL ontology or an ontology, you can map the data in the relational database against the schema, against the ontology, and automatically build and maintain a graph. And the problem is that today's developers who are developing Gen AI, they've not been in the AI world like some of us have for years, and they're not aware that they can do this. So they're just following, like lemmings off a cliff and just building another pinecone, vector database to do RAG. And it's pretty sad, actually. So this is the overall conceptual model. We store all of our content into a CMS. We create the graph automatically by, as I said, transforming the content into an RDF stream. We don't care what the content encoding is, like I said. It's based on mapping that RDF stream to the ontology. And then we enrich the graph with those additional domain-specific concepts. And now we have content as a service, truly AI, from a graph database, not from a vector database. Now, you can use this to augment an existing vector database, like I said. The typical way graphs are being used today by those who don't have the experience might be to create a graph and then use graph embeddings inside of a vector database, which doesn't overcome the predictive limitations of vector-based RAG models. They haven't yet discovered that they can either add or get rid of the vector database and replace it with a graph database to get the true deterministic AI. So here's a model where we do include a vector database, but we only use the vector database to inform the graph to say, well, the user asked a question and let's figure out semantically what they're asking. Maybe they're asking for how to do something. In that case, I'm going to be looking for task topics. or they're asking for how something works. In that case, I'm going to be looking for concept topics and so on and so forth. So we can combine traditional vector database technology with graph technology to get the best of both worlds, especially when we have to have retrieval from both structured componentized content like topic-based models and totally unstructured content that exists in our enterprise today. So finally, what we're looking at here is combining the best of both worlds, structured content with structured knowledge. We start at the bottom layer with our intelligent structured content or topic-based content. We create a virtual data graph out of it. We add the conceptual relationships for our specific domains, and then we can build semantic AI applications over that. And that's the beauty of this is, like I said, we're combining modular, semantically enriched topic-based content with structured-based knowledge graphs. It's structure plus structure. You couldn't ask for better synergy of two separate knowledge models that just go together like hand in glove. But to get this done, you're going to have to work together, team up with your AI ML engineers, with your people that know your knowledge management ontologies and knowledge graphs, and your content folks that understand your content base, which most of you, I think, in this room are. And there's things that we can do with this that are just incredible. We can do things that are unimaginable. In addition to auto-generating content, we can do things like neuro-adaptive documentation, where we can adapt content in real time to the cognitive and emotional state of the user. We can interrogate our entire content corpus and get information out of our corpus that we could never get even with a sophisticated content management system. And we really did it and now have a maintainable, automatable process to use deterministic knowledge graphs instead of predictive vector databases. So like I said, this paper is it's deep. It's really meant and designed for both content professionals and knowledge engineers and AI ML team developers, all to do that. You'll also find on my website, thinkingdocumentation.com, you will find several more related papers. One of them is 150 out-of-the-box queries that you can issue against the knowledge graph once it's created. Not just for retrieval, but to do things like find out where content is duplicated and reused. 150 queries that you can use immediately once you create your graph, and make that available on my download site as well. So I'm going to stop there. I don't know if I'm over time. I know the last presentation was a little bit over, and I hope that you found that interesting and useful.
Absolutely. And I think from the feedback, a lot of people are too. Michael, thank you very, very much. There were some questions in the chat. If you would be able to answer them in the chat or in separate chats, that would be really lovely. And thank you very much again.
Absolutely. Yeah. Auto classifiers, there's so many good tools out there today. We've been using GraphWise's Ontotext. We also use Pool Party, but there's others out there. The one caution I would say would be people might be confused because there's two classes of graphs. One is called a property graph. The other one is called an RDF graph. We prefer RDF graphs because they're open standard. They're interchangeable with each other, and most importantly, the two most is they truly, by most good ones, include an inference engine in the graph database, and they're best for linked data, which is what most of us on this call have. Whereas property graphs are super for doing RAG with unstructured data. So you might actually have a model where you use two different kinds of graphs, one for unstructured and one for structured content. And there's nothing wrong in hybrid models like that. I wanted to make sure that I got that point across because that's a question I get very, very frequently.
Thank you very much for the advice.